Stats with StatCat.
That's me. So if you've been learning about analysis of variance, a question that you might end up asking yourself is, why are we even doing this at all? Why don't we just do multiple t-tests if what we're wanting to do is analyse group differences? Now, it does seem reasonable to just do multiple t-tests, but it is statistically risky to do that. And that is why we make use of ANOVA. And in this video, I'm going to go through the reasons why that is. But to help explain it, we need to be aware of what type 1 error and type 2 errors are. So a type 1 error is where we reject the null hypothesis when it is actually true. And type 2 is failing to reject the null hypothesis when it is actually true. In other words, a type 1 error is where we conclude something is happening when it's not. So like a false alarm. A type 2 error is concluding something isn't happening when it is. To put it in more scientific terms, as an example, if there's, say, a drug trial, if we were to end up concluding that the drug works when it really doesn't, that is like a type 1 error. And a 5% false alarm rate, or you could also say false positive rate, that is the conventional criterion that gets accepted in scientific investigation. That is p less than 0.05. A type 1 error rate is the probability of a false positive happening for a single test, and the type 2 error rate is probability of a false negative for a single test. And importantly, the family-wise error rate is the probability of a type 1 error across multiple tests. And there's a little formula that you can use to work that out. And importantly, in simple terms, what you want to be aware of is that if you conduct multiple tests, it compounds the false positive chances. And the slide here, the chart on the slide here, indicates how as the number of statistical tests goes up, the chances of making that type 1 error pretty quickly goes up. So, which is not a good thing. So let's take a simple example of, say you wanted to examine, the efficacy of different drugs. And you might have a simple design where you've got 2 different drugs and a control group, and, with some sort of outcome measure. Now, after doing a simple study like this, you would be interested in comparing across the 3 groups. And so you could do multiple t-tests where you compare like the control versus drug A, control versus drug B, and drug A versus drug B. And you can do this, and you probably will end up doing this. However, something to be mindful of is that with 3 tests, if we apply that little family-wise error rate formula, what happens in a case of 3 tests is we would have a family-wise error rate of about 14%. And so therefore, there's about a 14% chance of getting at least one sort of false positive result, which is above that criterion of around 5% that we would like to maintain. So the solution to this is to, instead of just getting straight into those multiple t-tests, we can do an initial analysis of variance test that we conduct as a single omnibus test that, because it's only a single test, it maintains that 5% error rate. So we do that initially, and then if we get a statistically significant result of that ANOVA, it's only then that we proceed with doing multiple follow-up tests. Now, doing follow-up tests is a whole thing unto itself that would require a whole other video. But for the purposes of this video, I'm just illustrating why we do the initial ANOVA as the initial step. It's all about the family-wise error rate and sort of maintaining that 5% criterion. So, thanks for listening.